In previous videos, we have learned about the small signal models of DC-DC converters and also looked at some of the actually an introduction to basic linear control system theory. So in this video, we'll go ahead and use these models and the concepts in designing feedback controllers for DC-DC converters. In particular, we look at a technique called the K-factor method, which is fairly widely used in the industry for design of DC-DC converter controllers. Almost all the control techniques that we are going to study in these various videos, they can be grouped under this class of control methods called the loop shaping based control methods. So essentially we shape the transfer function of the loop gain or the open loop gain, specifically the Bode plot of the loop gain, to make sure that it has the desired characteristics based on the required control specifications. So the starting point of all of these loop shaping methods is to determine the desired crossover frequency, which in these videos we define as synonymous with the bandwidth. Okay, so this is the frequency at which the loop gain has a magnitude of 0 dB, or in absolute values a gain of 1. Okay. So the choice of crossover frequency, it can be obtained from the requirements on the dynamic performance, like what is the settling time required, for example, or what is the response time to step changes in the command reference, or more often it is dictated by the switching frequency related limits. So most often we will not have a bandwidth which is more than 1/10 of the switching frequency, and in most cases it is going to be much lower than this 1/10 of the switching frequency. Okay, so then we studied in a previous video that the steady state error depends on the DC gain of the loop gain. So higher the gain, smaller the error. And if you want zero steady state error as required in most DC-DC converter designs, then you should theoretically have infinite DC gain, and that is equivalent to requiring an integrator or 1/s term in the controller transfer function. So almost all the controllers that we design will have this integrator or this pole at the origin, 1/s term. Then to achieve the desired phase margin, we will see that at the crossover frequency, the phase of the loop gain without the controller zeros would have a phase lag more than what is required based on the phase margin consideration. So we will have to add zeros at appropriate frequencies, appropriate locations, to boost the phase so that we have the required phase margin, and that is part of the controller design. And after having done that, after having ensured that the phase at the crossover frequency is exactly what is needed, we will see that the crossover, the 0 dB point, does not exactly coincide with our specified crossover frequency. So we need to usually shift it up. The entire Bode plot has to be shifted up, and that is done by adjusting the constant gain in the controller to make sure that the crossover happens exactly at the specified omega c, or the crossover frequency. And in most cases, we know that, for example, if your objective is to control the output voltage, when we sense output voltage, we know that there is going to be a high frequency switching frequency ripple, and we may want to attenuate the magnitude of the switching frequency ripple when it enters the feedback controller. So so very often we will be required to have a high frequency pole below the switching frequency, so that it provides some attenuation to the high frequency ripple contained in the output voltage or the inductor current, whatever we are sensing. And I should also mention, in the choice of the bandwidth, there is one more consideration. We know that most DC-DC converters have a right of plane 0, and we know that it is fairly difficult to compensate for a right of plane zeros. So in those cases, we are better off having the crossover frequency well below the minimum right of plane 0. So we need to understand the transfer function of the plant and make sure and know where the right of plane 0 is located, and we know it's going to be changing with operating conditions. So find out the worst case and then determine the minimum right of plane 0 location and make sure the bandwidth is below that. Okay, so the K-factor method that we're going to study in this video is a type of loop shaping technique. And as I mentioned, it is widely used in the industry for DC-DC controller designs. One of the main attraction of the K-factor method is that it is very easy, very intuitive, and it is a clear step-by-step design method that is easy to implement in practice as well as in simulation. And also importantly, once we decided on what crossover frequency and what phase margin we want, then the K-factor controller can very accurately meet those phase margin and crossover. Unlike, for example, if you use a pole zero cancellation method, then you start with some value of desired crossover frequency and phase margin, but you will only get reach it approximately, not exactly, whereas K-factor can give you exact desired values of phase margin and omega c. The reference for the K-factor method is given here, a paper in the Proceedings of PowerCon, and also this was introduced by Dean Venable, and we can also refer to this website for more information on the K-factor method. So there are three types of K-factor based controllers that we'll be studying, widely used in the DC-DC controller design. The first one is the type 1, and it is a simple integrator with the gain Kc. Type 2 has the same integrator Kc over S. In addition, it has 1 0 at omega z and a pole at omega p, and the omega z has to be necessarily at a lower, it has to be lower than omega p. The 0 has to occur earlier than the pole. Only then we get a phase boost. And type 3 is once again the integrator, which is required in all the controllers for 0 steady state error. In addition, it has 2 zeros and 2 poles. Now both of these zeros, omega z, are at the same locations, and both the poles are also at the same location, omega p, but omega z has to be less than omega p once again to have a phase boost. Okay, so we need to study when to use each one of these types, and once you've chosen the type, how do you determine the values of Kc, omega z, and omega p. So first we look at how do you make the choice on the controller type. We know that the starting point of any design is to decide on the desired crossover frequency omega z and the required phase margin. So once we have that, then we can go ahead and determine the phase of the plant. So this is everything except the controller, which we have not yet designed, the phase of that. Okay? So that we define that as phi system, and we need to determine this phase at the crossover frequency that we have chosen. Okay? So if we know the analytical transfer function, for example, for a buck output voltage control, it is the D2VO transfer function. So if you know that, then you can calculate the phase of this transfer function, the phase angle, at the desired upon crossover frequency. If you don't have the transfer function, then we can use simulation and look at the phase exactly at this omega c. Okay, then we know that all the controllers, each of the three types that we have seen, they have an integrator or a pole at the origin, and we know that that introduces a 90 degrees phase lag. So that has to be considered in the design process. So the next step is to calculate the phase boost required. So the phase boost is provided by the pole zero combination, everything except the integrator. So we can determine what phase boost is required given this this phase lag of the plant, and the 90 degrees contribution from the controller, and the required phase margin. Okay. So the formula for the required phase boost is given here. So PM is the desired phase margin minus the phi sys, which is the phase of the entire plant except for the controller. So minus 90 degrees. That is the formula for the phase boost. So let's look at how that was obtained. Okay, so we know the definition of phase margin. So phase margin we derived earlier is the phase of the complete system. So the phase of the open loop OL at the crossover frequency omega c, okay, plus 180 degrees. Okay. So essentially phase margin is the how many degrees we are above the minus 180 degrees point. So that is the definition of phase margin. The phi OL, so the phase margin equals the loop gain, the phase of the loop gain can be written separately as the phase of the plant, which is this phi system. All of these are at omega c, so I will not repeat that. It's at omega c plus the phase contribution due to the controller alone, call that as phi c, plus this 180 degrees. Okay. And that would be phi system. The phase of the controller, we saw that all of them have this 90 degrees phase lag, so there is a minus 90 degrees component. And then what is provided by the pole zero pairs as the phi boost. Okay. So that is the minus 90 plus phi boost is phi c plus the 180 degrees from this equation. So this minus 90 plus 180 gives you plus 90, and then take the phi. So the phi boost then would be phi boost equals this PM, which is, we'll substitute the PM desired value. Okay, that's what we're designing for. Then this is plus 90 on this side, so that becomes minus 90 on the other side, and then we're left with this minus phi system. Okay, so that's exactly what we had here. Okay, so then once you determine the required phase boost from the controller, then use this table to decide on the type of controller needed. So if you do not require any phase boost, just 0 degrees, then type 1 is suitable. Type 1, recall that it only has an integrator, does not provide any phase boost, so it's not very widely used. But if you require a phase boost that is more than 0 but less than 90 degrees, then type 2 can be used. Type 2 has just one pole zero pair, and the maximum phase boost that you can get from a single pole zero pair is 90 degrees. Okay? And 2 pole zero pairs in the type 3 controller can give you as high as 180 degrees phase boost. Therefore, if you need phase boost 90 degrees and above but less than 180 degrees, then type 3 can be used. Okay, next let's go ahead and study how to design the different parameters needed in each type of controller. Type 1 is first. This is used when we don't need any phase boost and therefore doesn't have that many applications. The transfer function itself is shown here. It's Kc over S, and the corresponding Bode plot of just the controller alone is shown here. The magnitude plot is it has a minus 20 dB per decade slope throughout in the entire frequency range, and it reaches 0 dB exactly at Kc radians per second. And here is the phase plot. It is always minus 90 degrees phase lag and at all frequencies. So the objective is to come up with the procedure to calculate this value of Kc. The Kc can be obtained from the requirement on the crossover frequency omega c. So we know that at the desired crossover frequency omega c, the magnitude of the entire loop gain should be 1. Okay? So that is magnitude of GOL at j omega c should be 1. But GOL itself is the product of the GP, which is the plant transfer function at j omega c, and the magnitude of the controller itself. The controller is Kc over j omega c, and this product should be equal to 1. Okay? So that gives us the required expression for Kc. So Kc should be this 1 over GP j omega c, which is given here, times the magnitude of the times j omega c. Its magnitude is simply omega c. Okay? So that is the final expression for Kc. I should have actually written this as the magnitude here. It's the magnitude. Only then this becomes simply omega c. Okay, so this video is almost 15 minutes long, so I will take up the design of type 2 and type 3 in the next part of this video on K-factor design methods.